Hello everybody, welcome to another Cranky Calculus video. I'm your cranky classmate, here to help you with some more AP Calc A, B, and BC review. Today we're reviewing Unit 10, which is BC only, and we're specifically focusing on Convergence and Divergence and the Taylor and Maclaurin series. So we have a nice FRQ and MCQ ahead of us, so let's get started. So we have an FRQ here, and it gives us the Maclaurin series for a function f, and it wants us to find the values of f of 0, f prime of 0, and f double prime of 0. Now, they're kind enough to give us the first first three terms of the series, and using this we can actually find our values. So let's go ahead and get started. First value it wants us to find is f of 0. And this is really easy. This can literally just be done by plugging in 0 to all the terms. So if we plug in a 0 to the first term, we get a 1. If we plug in 0 to the second term, we get a 0 squared over 2 factorial. Oops, that is a really bad 2. There we go. And then if we plug it into the third term, we get 16 times 0 to the fourth over 3 factorial. And this is just equal to 1 because every subsequent term is going to have an x term, and we're going to plug in a 0 for the x term so that those terms are going to 0 out, and we're just left with this 1. So that was pretty simple. Now, to find f prime of 0, we first have to find f prime of x. And this can be done by literally just taking the derivative of the first three terms. So let's go ahead and do that. We'll label f prime of x as the derivative of the first term, which is 1. So that's derivative of 1 is 0. And then it's just power rule from here on out. So 2x over 2 factorial plus 4 times 16 is 64, x cubed over 3 factorial, and so on. And if we plug in a 0 to this, remember, this first term is 0, we plug in a 0 here, this term is going to 0 out, plug in a 0 here, this term is going to 0 out, and that's going to happen for all the subsequent x terms, and we're just going to be left with a 0. So again, pretty simple. Now we have to find f double prime of 0, and this can be done by just taking the derivative of the terms in the f prime series. So let's go ahead and do that. F double prime of x is equal to, our first term here would be 2x over 2 factorial, which would just be 2 over 2 factorial, and I'm just going to write this as 1, plus 64x cubed over 3 factorial, that's just power rule again. So I'm just going to write it like this, so I don't have to distribute out the 3. And so on and so forth. And again, it's a very similar thing. If we just plug in a 0, all of these subsequent terms are going to have an x term, where plugging in a 0 will cancel everything out, and we'll just be left with 1. So just to write over here, we have f of 0, which is equal to 1. That's an I, not a 1. Whoops. F prime of 0, which is equal to 0. And then f double prime of 0, which is equal to 1. There we go. That's part A of the FRQ done. Let's move on to part B. Okay, so part B wants us to find if f has a local maximum, local minimum, or neither at x equals 0, and wants us to justify our answer. Now, to find a local max or min, there's multiple ways we can do this. I think we should use the second derivative test, since we already found the value for the second derivative in the previous answer, or in the previous question. So that actually helps us a lot, because we can just copy down what we got in the first problem. So f of 0 is equal to 1, f prime of 0 is equal to 0, and f double prime of 0 is equal to 1. Now, remember, in order for the second derivative test to be true, we need x equals 0 to be a critical point at f prime. So, and we can see here that f prime of 0 is equal to 0, and critical points occur when the first derivative is equal to 0. So that's checked off, and we see here that f double prime gives us a positive value of 1. So using this information, we can use a second derivative test to determine that that f of x has a local minimum at x equals 0. So we can say that f has a local minimum at x equals 0 because f prime of 0 equals 0 and f double prime of 0 is greater than 0, or it's positive. So that's part B, pretty easy. Let's move on to part C. Okay, so part C wants us to find the interval of convergence of the Maclaurin series for f. And so I went ahead and wrote f of x in its series form. And remember, to find the interval of convergence, we need to use the ratio test. So let's go ahead and do that. The first step in doing the ratio test is writing your limit. So I'm going to write the limit as n approaches infinity of, remember, it's the absolute value, and we have to add 1 to all the n terms. So x to the 2n plus 1 over n plus 2 factorial times, remember we flip now, so n plus 1 factorial over x to the 2n. And this may seem a little complicated, we might not know where to go, but let's go ahead and keep simplifying. So we're going to write this is equal to, again, don't forget your limit notation. That is a very bad infinity sign, I am sorry. Don't forget your limit notation. We're going to distribute this 2 to the n plus 1, so we're going to get x to the 2n plus 2. And I'm actually going to rewrite this n plus 2 factorial over here. I'm going to rewrite it as n plus 2 times n plus 1 factorial. Because remember, these are mathematically equivalent. And then I'm going to write our original function in reciprocal form. And if you look here, we can actually already cancel out, I'll do that in red just to make it a little bit clearer. We can actually cancel out these n plus 1 factorials and go ahead over here and rewrite our limit statement as the limit as n approaches infinity, the absolute value of, I'm going to rewrite this x squared, x to the 2n plus 2 as x to the 2n times x squared. And you'll see why in a second. Remember, all over n plus 2 times, and since we canceled out that n plus 1, we're left over with the 1 on top and x to the 2n on the bottom. And again, here we are able to just cancel out these x to the 2n's, and let's go ahead and rewrite our limit, which is equal to the limit as n approaches infinity of the absolute value of x squared over n plus 2. And one thing we can actually do now is pull out this x squared, because remember, we're only trying to find the limit as n approaches infinity, so we can actually just pull out the x squared. We'll get x squared times the limit as n approaches infinity, oh, don't forget your absolute value here, of 1 over n plus 2. And we know that since it's going to be 1 over infinity, this is just going to approach 0. So we know that this limit is equal to 0. And because 1 is always going to be greater than 0, this limit will actually, or the interval will actually be from negative infinity to infinity, meaning that the series converges everywhere. So we can go ahead and write this over here. Let me just zoom out. We can go ahead and write that f of x converges for all real numbers. Or you can write from negative infinity to infinity. It doesn't really matter. They mean the same thing. But that is your Unit 10 FRQ done. Let's go check out some MCQs.
Hey guys, it's another cranky classmate here, and we are going to do the Unit 10 MCQ. So we have number 2 here. Find a power series for the function f of x is equal to 4 over 2 minus x squared, centered at x equals 0. Well, this series is in the form of 1 minus x, which is the geometric one. So we need to manipulate this f of x so that it looks similar to this and has the 1 minus and then our r value. So we can manipulate this by saying it's actually 4 times 4 over 2 times 1 minus, and then we turn the x squared into x squared over 2. And then by doing this, we can actually simplify here and cancel this out, make this a 2, and then the x squared over 2, remember, is our r value. So then it becomes x squared over 2 whole to the n. And then we need to multiply everything by 2 again because of this 2 at the top. So then when you simplify everything and distribute the exponents, we get 2 times x to the 2n over 2 to the n. And because 2 and then 2 to the n have the same base, they're going to simplify together to form 2 to the 1 minus n, because 2 is just 2 to the 1. And then when you divide, you subtract the n. And then you have x to the 2n once again. And then that's only going to match up with b, and that's going to be our answer. So the next one, the coefficient of x to the 6th in the Maclaurin expansion for f of x is equal to 2x whole squared times cos x is, and in order to do this, we need to Maclaurin expansion cos x first. So we have cos x is equal to, and then if you remember, the cos x expansion is actually 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And I'm pretty sure we don't even need to keep going because you'll see why. So the 2x whole squared is actually going to be 4x to the squared. They just put it in that form to trick you. So then when we do 4x cos x, we just multiply this entire expansion times 4x squared. So then that becomes 4x squared minus 4x to the 4 over 2 factorial plus 4x to the 6th over 4 factorial. And remember, we need the x to the 6th term, so that's right here. So then we need to find the value of 4 over 4 factorial, which is just going to be 1 over 6 being our answer. All right, number 4. Given that the arctan Maclaurin expansion is x minus x to the 3rd over 3 plus x to the 5th over 5 and then minus x to the 7th over 7 and so on, find the Maclaurin series for the integral of x arctan x dx. So first we need to find x arctan x, and that's going to be, we're going to be multiplying the arctan here times x. And that's going to be pretty simple. We're going to be having x squared minus x to the 4th over 5 minus, sorry, not over 5. That's going to be over 3 plus x to the 6th over 5. And then we just need to take the integral of this, because that's what it asks. And when we do that, we have x cubed over 3 minus x to the 5th over 15, because we need to multiply that 5 and 3 denominator, and then plus x to the 7th, and then same thing, we need to have a 35 here. And the only thing that matches up with, oh, don't forget plus c. Actually, you don't really need to, because all of them have plus c's. But anyways, the only one that matches that is a here, and that's going to be our answer. Next one. Find c that the sum of the following series has a given sum. 2c over 5 to the n is equal to 4. Okay, so looking at this is pretty clearly in the form of a geometric series. So then our sum is just going to be, our sum is going to be a over 1 minus r is equal to our sum, which is 4. So what is a, what is r? A is the first term in the series, and that's not always when n is equal to 1 or n is equal to 0. That's whenever this value is, and in this case it's just 1. So we can plug in 1 for n, and that's going to be our first term. So we have our first term, which is just 2c over 5, and then over 1 minus our r value. And if you remember in a geometric series, it's going to be in the form of r to the n, and so that means our r is still our 2c value. So then that's going to be equal to 4. So then we can simplify everything. And we're going to say 2c over 5 is equal to 4 minus 4 over 2c over 5. And then when we simplify everything, it's just going to be 2c is equal to 4, and then c is equal to 2. I did the algebra pretty quick here, but I think you guys are smart enough to get that. Next question, use a Maclaurin expansion to estimate the first 3 non-zero and non-constant terms of the integral of e to the x squared. So first, to do this, we need to do the Maclaurin expansion for e to the x, and that's going to be 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial. So then we need to do x or e to the x squared, and to modify this, we need to plug in x squared for all of the x's, meaning that we're not multiplying by x squared, we're actually substituting all of the x's in. So then this 1 does not become x squared, it just stays as 1. And then when we substitute x squared for this x here, it doesn't become x cubed, it stays as x squared. And then we just keep plugging in for x here. So then we have x squared to the 2, which becomes x to the 4th over 2 factorial, plus, and then we have x to the 3rd, we plug in x squared, we get x to the 6th over 3 factorial. So then we need to integrate that, and then when we integrate that, we get x plus x cubed over 3 plus x to the 5th over 2 factorial times 5, which becomes 10. So then our final answer here will match up with A. This is going to be our answer. So this next question, which of the following series diverges? And we're given a bunch of series. So this first one we're going to put in the form of 1 over 5 to the n. And if you remember about geometric series, when the absolute value of our r is less than 1, then we are converging, and that's the case here. So we are converging. Okay, this next one is going to be alternating series test, and it's alternating, decreasing in magnitude, and appears the limit is equal to 0. So we can x out this -1 to the n, and then we're left with this series right here. And when we find the limit, the limit is going to approach 0, which means that we are converging. And the next one is also alternating series test. It's alternating and decreasing in magnitude, and the limit is equal to 0. We can x this out. So we're left with this right here. And that also approaches 0. So we're going to also be converging. Now this next one, we don't actually have to use alternating series test, even though it looks like it. We can just use nth term test, because the limit of this function when n approaches infinity, it's actually not going to be 0. It's going to be a different value. It's going to be 1/5, because we have this -1 to the n doesn't affect the limit per se. And what affects the limit is the fastest growing terms, which is going to be our n and then 5n. And then when we divide those, it's going to be 1/5. And that is not equal to 0, which means our nth term test determines that it diverges, which means our answer is D. Alright guys, thanks for watching this last unit review video. I hope you guys do well on your AP test, and I hope that all of these unit review videos that we've done so far have been beneficial. Thank you.